Welcome back to our series on alkene reactions. In this video, we focus on 1,2-dihydroxylation, an important transformation that converts alkenes into glycols, or 1,2-diols. The net result is addition of two hydroxyl groups across a CC double bond. Unlike the anti-addition seen with halogenation, osmium tetroxide delivers strict syn stereoselectivity through formation of a cyclic osmate ester. Our goal is to walk through the key steps that give the concerted syn addition of the two OH groups. For illustration, we will use 1-methylcyclohexane as the substrate and predict the product and its stereochemistry. Dihydroxylation with OsO₄ is a concerted syn addition. The two new COH bonds form simultaneously on the same face of the alkene. Starting from 1-methylcyclohexane, two new stereocenters are created at carbons 1 and 2, producing 1-methylcyclohexane 1,2-diol with the two hydroxyl groups cis to each other. Because OsO₄ can approach either face of the alkene with equal probability, that cis-diol is typically obtained as a racemic pair of enantiomers unless a chiral influence is present. Mechanistically, we describe two stages for clarity. First, the concerted formation of a 5-membered cyclic osmate ester. Second, hydrolytic or reductive cleavage of that ester to release the diol. The first stage is concerted and stereospecific. It is the origin of the syn relationship between the two OH groups. Stage 1. Concerted syn addition. Cyclic osmate ester formation. The alkene approaches the electrophilic OsO₄. The pi electrons of the CC double bond simultaneously interact with two oxygen atoms on OsO₄. Concurrently, OSO bonding is reorganized, and the osmium center forms two new bonds to the former double bond carbons. The result is a stable, 5-membered cyclic osmate ester in which both CO bonds have been formed on the same face of the original alkene, locking in syn stereochemistry. Stage 2. Cleavage of the ester, hydrolysis to the glycol. The cyclic osmate ester is then cleaved by treatment with a mild reductant in water. Typical workup reagents include sodium bisulfite or sodium thiosulfate. These agents break the OSO bonds and release the cis-1,2-diol. Note that this reductive hydrolysis reduces osmium. To operate catalytically, the reduced osmium species must be reoxidized by a co-oxidant such as NMO, H2O2, or NaIO4 to regenerate OSO₄. This video covered the syn dihydroxylation of alkenes using OsO₄ to yield a cis-1,2-diol. We will now briefly introduce two other reactions, the KMNO4 pathway and the m-CPBA pathway, to provide a comparative learning scenario. The first reaction is highly analogous to the OsO₄ reaction, and crucially, it achieves the same stereochemical outcome, syn dihydroxylation. Here is how it works. The permanganate ion, MnO4-, undergoes a concerted cycloaddition with the alkene's double bond. Because this is a syn addition, both new CO bonds form simultaneously from the same face of the alkene, resulting in a 5-membered cyclic manganate ester intermediate. Finally, the intermediate is cleaved by cold, aqueous base, breaking the MnO bonds to release the cis-diol product. In contrast, The second reaction sequence achieves the opposite stereochemical outcome, anti-dihydroxylation. First, the alkene is converted to a three-membered strained epoxide ring by m-CPBA, which fixes the initial CO orientation. Then, the epoxide is opened via an SN2-like backside attack by the nucleophile, OH-. This action forces the two hydroxyl groups to add to opposite faces of the ring, ultimately yielding the trans-diol product. Let's summarize. OsO₄ performs a concerted syn addition across the CC double bond via a cyclic osmate ester intermediate. With 1-methylcyclohexene, the initial step forms the cyclic osmate ester of 1-methylcyclohexane 1,2-diol. The cyclic osmate ester is cleaved, hydrolyzed, to the cis 1,2-diol. The final product from 1-methylcyclohexene is 1-methylcyclohexane 1,2-diol, which is obtained as a racemic pair of enantiomers in the absence of chiral control. Let's organize by keywords. 1,2-dihydroxylation is the addition of two hydroxyl OH groups across an alkene double bond to form glycols 1,2-diols. The cyclic osmate ester is the 5-membered intermediate formed during the OsO₄ catalyzed dihydroxylation reaction. The initial step of the OsO₄ and KMnO₄ dihydroxylation reactions proceeds via a concerted syn addition mechanism. To wrap up, those who wish to deepen their understanding of OsO₄ catalyzed 1,2-dihydroxylation and its related reactions are encouraged to study the following topics. If this video was helpful, we'd really appreciate it if you could share it with others. See you in the next reaction.